In this video, we will practice integration using partial fractions. This is a BC-only topic. If you haven't watched the previous video where I introduced the concept of partial fractions, you should definitely watch that first. You can either click the link that appears in the upper right-hand corner or find the link in the description. This is a practice video, so I'm going to skip some steps and assume you have a basic understanding of partial fractions already. We can tell that we are going to need partial fractions because substitution would not work, and the degree of the denominator is bigger, and the denominator is factorable. Before we can use partial fractions, we first need to factor the denominator like this. Partial fraction decomposition means rewriting the integrand as a over 3x plus 1 plus b over 3x minus 1. To solve for a and b, let's multiply both sides of this equation by the common denominator 3x plus 1 times 3x minus 1. If we multiply the left side of the equation by this common denominator, both factors cancel out and we are left with the 2. If we multiply this middle term by 3x plus 1 times 3x minus 1, the 3x plus 1 cancels out, and we are left with a times 3x minus 1. When we multiply the second term by 3x plus 1 times 3x minus 1, the 3x minus 1's cancel out, and we are left with b times 3x plus 1. There is more than one way to solve for a and b. But when we have linear factors like 3x plus 1 and 3x minus 1, it is usually easiest to pick a value of x that will cancel out one term at a time. For example, if we set 3x plus 1 equal to 0 and solve, we get negative 1/3. That means if we let x equal negative 1/3, 3x plus 1 will equal 0. So this term will be canceled out. That leaves us with 2 on the left side of the equation. On the right side we have a times 3 times negative 1/3 minus 1. So we have 2 is equal to a times. The 3's cancel out and we are left with negative 1 minus 1, which is negative 2. So we end up with 2 is equal to negative 2a. Dividing both sides by negative 2, we get a equals negative 1. If we set 3x minus 1 equal to 0, we get x equals 1/3. So if we let x equal 1/3, then 3x minus 1 will become 0. So that will cancel out this term. That leaves us with 2 equals b times 3 times 1/3 plus 1. The 3's cancel out and we are left with 1 plus 1. So that means 2 is equal to 2b. Dividing both sides by 2, we get b equals 1. Substituting negative 1 for a and 1 for b, we can now rewrite the original integral using our partial fraction decomposition. So we have the integral of negative 1 over 3x plus 1 plus 1 over 3x minus 1 dx. Now we can integrate term by term. The negative 1 in the numerator comes out in the front as a negative sign. So really we have the integral of 1 over 3x plus 1. We need to be careful because this will be a mental u substitution. If u is 3x plus 1, then u prime is 3. So we always have to divide by u prime. That's why we will have a 1/3 out in the front. Now, the integral of 1 over u is the natural log of the absolute value of u. But that is the absolute value of 3x plus 1. Moving on to the next term, Again, here comes a mental u substitution. If u is 3x minus 1, then u prime is 3. So we have to divide by u prime. We divide by 3, which gives us a 1/3 out in the front. Now the integral of 1 over u is the natural log of the absolute value of u. In other words, the absolute value of 3x minus 1. Don't forget the constant of integration plus c. This is one form of the answer, and on a free response question, this would be just fine. But just in case you run into something like this on a multiple choice question, let me show you how we can simplify this using properties of logarithms. First of all, notice that both terms have a 1/3. So let's factor that outside of parentheses. Then we have this. Reversing the order of the terms gives us this. Remember that the natural log of p minus the natural log of q is equal to the natural log of p over q. Similarly, the natural log of 3x minus 1 minus the natural log of 3x plus 1 is equal to the natural log of 3x minus 1 over 3x plus 1. So this is the answer that you would most likely see on a multiple choice question. Number 8. We know we will need partial fractions because the degree of the denominator is greater and normal use substitution will not work. The first step is to factor the denominator. 3x squared factors as 3x times x, 1 factors as 1 times 1. Inner, we have 1x. Outer, we have 3x. To get a middle of -2, we need a positive 1 and a -3. So that means plus here and minus here. Next, we rewrite this integrand in the form a over 3x plus 1 plus b over x minus 1. To solve for a and b, we need to multiply both sides of the equation by the common denominator 3x plus 1 times x minus 1. On the left side of the equation, both factors cancel out and we are left with 3 minus x. When we multiply the middle term by the common denominator, the 3x plus 1 cancels out and we are left with a times x minus 1. When we multiply the common denominator by the last term, the x minus 1 cancels out and we are left with b times 3x plus 1. We can solve for a and b by plugging in values of x that will cancel out one term at a time. If we set 3x plus 1 equal to 0 and solve, we get -1/3. So if we let x equal -1/3, this term will go to 0. Plugging -1/3 in for x here and here gives us this. 3 is the same as 9 over 3, minus a negative is a positive, and 1 can be written as 3 over 3. So on the left side we have 10 over 3 is equal to a times -4 over 3. In other words, -4 over 3a is equal to 10 over 3. Multiplying both sides by 3 cancels out the 3. And then if you divide both sides by -4, you get a is equal to 10 over -4. But this reduces to -5 over 2. If we let x equal 1, right here we have 1 minus 1, which is 0. So this term is canceled out. Plugging in 1 for x right here, we have 3 minus 1, which is 2. And then on the right hand side we have b times 3 times 1 is 3, plus 1 is 4. In other words, 4b equals 2, which means b is equal to 1/2. Let's substitute -5 over 2 in for a and 1/2 in for b to write the partial fraction decomposition of the integrand. So we have -5 over 2 over 3x plus 1 plus 1/2 over x minus 1. Now we can just integrate term by term. Start by taking the negative 5 over 2 and putting it out in the front. So really we have the integral of 1 over 3x plus 1. We can integrate that using mental u substitution. If u is 3x plus 1, then u prime is 3. So we wind up dividing by u prime. So we have to divide by 3. We can accomplish that by putting a 1/3 out in the front. So if we have the integral of 1 over u, we know that will be the natural log of the absolute value of u. But in this case, our u is 3x plus 1. Similarly, we put the 1/2 out in the front for the next term. Think of this now as the integral of 1 over x minus 1. So that's going to be natural log absolute value of x minus 1. Again, that was really a mental u substitution, but if u is x minus 1, u prime is 1, and dividing by 1 changes nothing. So here's the final answer for number 8. For number 10, notice that the degree of the numerator is greater than the degree of the denominator. That means we need to do one extra step, long division. You set up the long division like this. I'm noticing that the numerator is missing the x squared term, so I'm including a 0x squared here as a placeholder. X to the third power divided by x squared is x. So we start by putting an x right here, and I like to line up my like terms. Then you take the x and you multiply by the divisor. So x times x squared is x to the third power. X times x is x squared. And x times negative 2 is negative 2x. And then we subtract. X to the third minus x to the third is 0. 0x squared minus x squared is negative x squared. Negative x minus negative 2x is the same as negative x plus 2x, which is plus x. 3 minus nothing is 3. Then we sort of start over. Negative x squared divided by x squared is negative 1. So we put a negative 1 up top. Now take the negative 1 and multiply it by the trinomial. That gives us negative x squared minus x plus 2. And then we subtract. Negative x squared minus negative x squared is 0. Negative x minus negative x is negative x plus x, which is 2x. And 3 minus 2 is 1. We have already reached the constant term up top here, so you know that whatever's left is the remainder. And the way we handle that is we put a plus, and then you put the remainder, 2x plus 1, over the divisor, x squared plus x minus 2. This new integral is equivalent to the original integral, so we should be able to integrate term by term. But let's plan ahead a little bit. Will we be able to integrate this third term using u substitution, or do we need to use partial fractions? Well, if we let the denominator be u, then u prime will be 2x plus 1. And that's what we have in the numerator. So it looks like normal u substitution will work, and we don't actually need partial fractions. The antiderivative of x is 1/2 x squared. The antiderivative of negative 1 is negative x. And then I've left the integral of the third term so we can focus on the u substitution that we need to do. As I mentioned a moment ago, if we let u equal x squared plus x minus 2, then u prime equals 2x plus 1. Performing the substitution gives us this, but instead of dx, we write du over u prime. In other words, du over 2x plus 1. And of course, the 2x plus 1 in the denominator cancels out the 2x plus 1 in the numerator. So this integral is really the integral of 1 over u, which we know is the natural log of the absolute value of u. Substituting the trinomial back in for u gives us the final answer. If you accidentally integrated using partial fractions, you did it the long way, but you still can get the right answer, and it would look something like this. We will need partial fractions on number 12 because u substitution will not cancel out the x plus 2. We start by rewriting the integrand with the denominator factored. We need to rewrite this integrand in the form a over x plus b over x plus 5. We can solve for a and b by multiplying both sides of this equation by the common denominator x times x plus 5. If I multiply the common denominator on the left-hand side, the entire denominator cancels out, and we are left with just x plus 2. If I multiply the common denominator times the middle term, the x's cancel out, and we are left with a times x plus 5. If we multiply the common denominator times the last term, the x plus 5's cancel out, and we are left with b times x. If we let x equal 0, the last term disappears. So plugging in 0 for x leaves us with 2 on the left-hand side. So we have 2 equals a times 0 plus 5, which is just 5a. Dividing both sides by 5, a is equal to 2/5. If we let x equal negative 5, negative 5 plus 5 is 0, so this term goes away. Negative 5 plus 2 is negative 3, so we have negative 3 on the left. On the right we have b times negative 5, which is negative 5b. Dividing both sides by negative 5, we get b equals 3/5. Putting 2/5 in for a and 3/5 in for b, we can rewrite the integral using our partial fraction decomposition. Let's integrate term by term. Take the 2/5 from the numerator and just put that out in the front. So this is really the integral of 1 over x, which is just the natural log of the absolute value of x. Take the 3/5, put that out in the front, and this is really the integral of 1 over x plus 5. Technically this is a u substitution that we're doing mentally, but u is x plus 5, so the integral will be the natural log of the absolute value of u. Normally we have to divide by u prime, but u prime would just be 1, so that doesn't change anything. And don't forget your plus c. So that's the final answer for number 12. Often when we have trig functions being added or subtracted, we end up needing to do u substitution and then partial fractions. So let's let u equal sine x. In that case, u prime will be cosine x. Performing the substitution gives us this, but instead of dx we write du over u prime. In other words, du over cosine x. We notice that cosine x cancels out. So now we are left with this expression, which we will need partial fractions to integrate. We start by rewriting the integrand with the denominator in factored form. Now we need to rewrite the integrand in the form a over u minus 1 plus b over u plus 4. We can solve for a and b by multiplying both sides of this equation by the common denominator u minus 1 times u plus 4. If we multiply by the common denominator on the left, the entire denominator cancels out, and we just have 5. If we multiply this common denominator by the middle term, the u minus 1 cancels out, and we are left with a times u plus 4. If we multiply the common denominator times the last term, the u plus 4 cancels out, and we are left with b times u minus 1. If we let u equal 1, this term goes away. So we are left with 5 is equal to a times 1 plus 4. That's 5a. Dividing both sides by 5, we get a is equal to 1. If we let u equal negative 4, then this term goes away. That leaves us with 5 is equal to b times negative 4 minus 1. That is negative 5b. Dividing both sides by negative 5 gives us b equals negative 1. Putting 1 in for a and negative 1 in for b, we can rewrite the integral with a partial fraction decomposition. Integrating term by term, we have the natural log of the absolute value of u minus 1 minus the natural log of the absolute value of u plus 4 plus c. Before we put sin x back in for u, let's simplify using the properties of logarithms. Remember that natural log p minus natural log q is equal to natural log p over q. So we can rewrite this expression as the natural log of the absolute value of u minus 1 over u plus 4. Substituting sin x back in for u gives us this for the final answer. Here's another situation where we first need to do u substitution and then partial fractions. If we let u equal tangent x, then u prime will equal secant squared x. We see the secant squared in the numerator, so this is promising. Doing the substitution gives us this. Instead of dx, we write du over u prime. In other words, du over secant squared x. Then we notice that the secant squared in the numerator will cancel out the secant squared in the denominator. So now we have this, but we will need partial fractions to integrate. We need to rewrite this integrand in the form a over u plus b over u plus 1. To accomplish this, we need to multiply both sides of the equation by the common denominator u times u plus 1. When we multiply on the left, the entire denominator cancels out, and we are left with 1. When we multiply the middle term by the common denominator, the u's cancel out, and we are left with a times u plus 1. When you multiply the second term times the common denominator, the u plus 1 cancels out, and you are left with b times u. To solve for a and b, we must pick values of u that will cancel out one term at a time. For example, if we let u equal 0, this term goes away. That leaves us with 1 is equal to a times 0 plus 1. In other words, a is equal to 1. If we let u equal negative 1, this factor becomes 0, so this term goes away. We are left with 1 is equal to negative b. Dividing both sides by negative 1, we get b is equal to negative 1. Now that we know that a is 1 and b is negative 1, we can rewrite the integral using our partial fraction decomposition. Integrating term by term gives us this. Before we substitute tangent x back in for u, let's use the properties of logarithms to simplify this expression a little bit. Remember that natural log p minus natural log q is equal to natural log p over q. So natural log u minus natural log u plus 1 is the same as natural log u over u plus 1. Substituting tangent x back in for u gives us the final answer. Find the area of the region bounded by the graphs of the given functions. Let's start by rewriting this rational function in factored form. I don't know exactly what this graph looks like, but I know it has vertical asymptotes at x equals -2 and x equals -3. But we don't really need to worry about that because we are looking for the area of the region bounded by y equals 0, x equals 0, and x equals 1. So that puts us in this zone in the first quadrant. Notice that for positive values of x, we are going to get a positive y value. So we don't have to know exactly what this graph looks like. All we need to know is that it is above the y-axis in this region. The area under this curve from 0 to 1 is just the integral of this rational expression from 0 to 1. This is not an integral we can find by substitution, so let's use partial fractions. We can solve for a and b by multiplying both sides of the equation by the common denominator x plus 2 times x plus 3. If we multiply the left side of the equation by x plus 2 times x plus 3, the entire denominator cancels out, and we are left with just 12. If we multiply the middle term by the common denominator, the x plus 2 cancels out, and we are left with a times x plus 3. If we multiply the last term by the common denominator, the x plus 3 cancels out, and we are left with b times x plus 2. We can find a or b by plugging in a value of x that will make one term disappear. For example, if we plug in -2 right here, we get a 0, which will make this term go away. So let's start by letting x equal -2 and see what happens. On the left side, we still have 12, but then we have a times -2 plus 3. That's 1, so that means 12 is equal to a. If we let x equal -3, then we get a 0 right here, and this term goes away. That leaves us with 12 is equal to b times -3 plus 2, which is -1. In other words, -b. Dividing both sides by -1 gives us b is equal to -12. Now that we know that a is 12 and b is -12, we can rewrite the original integral using our partial fraction decomposition. Let's integrate term by term. Take the 12, put that out in the front, which leaves the integral of 1 over x plus 2. That's the natural log of the absolute value of x plus 2. Bring the -12 out into the front. That leaves the integral of 1 over x plus 3. That's the natural log of the absolute value of x plus 3. Then we apply the limits of integration from 0 to 1. Before we evaluate, let's simplify this as much as we can. Remember that we are only dealing with the first quadrant, so these are going to be positive values of x. So we don't actually need the absolute value symbols going forward. Let's start by factoring out this 12. So now we have this. Let's use the properties of logarithms to simplify this a little further. Remember that the natural log of p minus the natural log of q is equal to the natural log of p over q. So the natural log of x plus 2 minus the natural log of x plus 3 is the same as the natural log of x plus 2 over x plus 3. Now we can apply the limits of integration. We need to find the value at 1 minus the value at 0. If we plug in 1 for these x's, we get 3 over 4. If we plug in 0, we get 2 over 3. So this is one version of the answer, but let's simplify a little bit. So here's another version of the answer, but we can use this same property of logarithms to simplify again. So here's another version of the answer, but when you divide by a fraction, you multiply by the reciprocal. And that gives us this. So the final answer is 12 natural log 9 over 8.